Hello, hello. Welcome to the stream. Hope y'all are having an excellent day. Excellent day. We've got an awesome stream for you planned today. We're going to finish off our journey with this prototype. And the... Hello, No Corp. Yeah, this is the final piece because this circuit over here has already been obsoleted. We're going to do a full duplex RS-45. We're doing half duplex now. But anyways, yeah, this is taking in the battery voltage, stepping it down to 24. It's going to be sweet. It's going to be a lot of fun. Just got a couple more parts to get on there. I got all the lame ones on there before. So we got a couple FETs, a couple caps, and we should be off to the races. Yes, I'm pumped. I'm pumped. Yeah. And we're going to do the usual suite of tests, line load, regulation, all that fun stuff. So, yeah. This should be awesome. Alright, let's get these FETs on there. So this controller called for an external FET to go in parallel across the synchronous rectifier. Oh, wait a minute, I don't think I said that right. An external rectifier diode to go across the synchronous FET. Pretty sure I said that backward the first time. Anyways, I thought that was pretty weird. Like, that's pretty bizarre. Basically, why is this is doing adaptive dead time control, which usually awesome. Hopefully, it's awesome in this controller. Where basically it waits for the body diode to be forward biased before it switches on the FET. So in order to keep maximum efficiency, you kind of get a best of both worlds situation with this, where you got a Schottky diode rectifying you until you enhance the diode, or enhance the FET, but until you do that, you've only got 0.1, 0.2 volts dropped across it instead of like 0.7. So, I don't know if I really want to put that FET in there. I think I'll keep it for now because that's how it was designed, but I just don't know. It seems a little unnecessary. Then again, we are pumping 24 volts and a fair chunk of current through it, so efficiency will be kind of important. Yeah. As always, I'm nervous you guys can't hear me. Let me know if the audio's good, or at least acceptable, and that'll help me sleep at night. Yeah. Welcome. Cool. So, tested. Oh, thanks, NoCorp. Thanks, guys. You dropped a comment on the channel a couple of minutes ago on the last video. Just a question mark. Was that like a where are you? Or was that a why are you releasing this video? Because either way, I think I've got an answer for you. Just curious. Schottky diodes. Yeah. Alright, got the diode, got the FETs, got the inductor. Those output caps are hanging around here somewhere. There they are. Underneath my schematic. Oh, look at that. We are out. Sweet. Alright, we got our 2 output caps, inductor, all that fun stuff. Break out the hot air gun. We'll be done in no time at all. Oh! Okay. Thanks, man. What probably happened is YouTube flagged it because it was a link and it hid that. So I have to dig into these are flagged for review. I will have to do that. I don't know why. They don't give me notifications when comments get flagged for review, which seems really silly because I'm supposed to review them. So they just disappear. Thank you. I'll take a look at that. I'll take a look. Yeah. Like, here's this comment that's flagged for review. Oh, wait. Nope. Maybe next year. It was, what did you say it was? Massive ferrite core? Holy crap. How massive is massive? Is this like the size of your face or like the size of your fist? Either way, it's probably super cool. I'm just curious. Yeah, I mean, it all comes down to material. It depends on what you're doing. I'm sure you picked it right. Is that like a modern MPP core, or is that a like a traditional transformer core for line frequency magnetics? Alright. Yeah, it could be. Oh, that was yes, no corporation suggested Maybe they're similar to what's on AliExpress. I think that's likely. Yeah. I'm sure you could do a lot with something like that. It would just kind of scare me because I like it when things come with data sheets. Then again, maybe they do give you data sheets. I've actually been a huge fan of LCSC. I don't know if you guys are aware, but they're affiliated with JLC PCB. And what I love about them is that they give you access to a lot of the same parts that you'd find on like AliExpress, like the made in China components that might be clones, whatever. But they're from genuine silicon manufacturers over there, and they're actually an authorized distributor of all those cheap Chinese, potentially knockoff ICs. And I'm like, yeah! Yeah! Cheap components with data sheets. Exactly. Yeah. And there's some parts that you just can't find here, like on the Arduino Nanos. If you look on the bottom, they've got a cheap USB to TTL converter. I forget the part number. But you try to find that in America, and not a chance. Not a chance. You can't find it from DigiKey, you can't find it from Mauser. LCSC though, oh, they'll ship it to you. They'll ship it to you. So it's pretty cool. It's pretty cool. Yeah, I'd probably be more inclined to use an LCSC than an AliExpress or an eBay part. But I have seen even like Epcos or Meg Inc. I've seen those ferrite cores like on eBay, on Amazon. I'm like, what are these doing here? What in the world even is this? But I mean, at that point you're just buying a part, so I'm sure those are fine. Yeah. Do they actually bundle shipments from JLC PCB and LCSC? I've never tried to do that, but yeah, I mean their shipping is pretty reasonable. You can save like that TTL converter I was mentioning from LCSC. That thing, I think if you bought the FTDI equivalent, it's like $5 a part. You compare that to the cheaper Chinese version, and that's like 20 cents a part. You could easily save the $15 you're going to. Oh, okay. If if you have an order code, you can. That makes sense. I'm confident that if you're building the right sort of thing, if you really plan to use LCSC, I'm betting you could save enough in your components to get back your shipping. Never done it, but from what I've heard from other people in the community, like they just do good business. Tested says, oh, that's pretty big. B50, okay. Yeah. Do you know who made what B50 core material? Is that from Epcos, or do you know who that material is from? So I feel like everyone's got their 11 herbs and spices that they put into their magnetics. Hello, JD. Hot air temp 335C. I don't know. Probably. Is that? Can you see it? Oh yeah, you can. Yeah, 335C. Yeah, that's right. Yeah, I just turned it up until I could solder well. Yeah. It's not an exact science. It's more of like a. I know that it needed to be above 300 to melt my solder, and so I just kind of creeped it up until I was able to reflow components in a reasonable amount of time. Good question, though. Good question. I can look into that. Without knowing the vendor, it might be kind of hard to really evaluate the core. But if we can figure out who the material's from, then we can pull like the manufacturer information. In fact, the manufacturer might have I think I've mentioned simulators for it. Yeah. Yeah, my airflow rate's a little bit high. At least I think it's a little high. But the reason why is because with this particular hot air station, it's kind of known for burning itself out. And so if you set the airflow too low, it actually overheats the coil, which is not ideal. But it gets the job done. Alright. I'm just gonna go from enough solder to way too much solder on these pads. Just want to make sure I'm getting them connected well. Okay. That diode is a TVS that is optional. Yeah, I'll see what I can do. I'll see what I can do for you, Tested. I'm confident that there's some information out there that we can glean, but it might come down to a little bit of experimental verification. Pump some power through, and look at like what kind of leakage inductance you're getting. Might be able to do something like that. I don't know. Cause I'll have to think. I'll have to think about ways to experimentally determine what core material you have, or the properties of the core material. Yeah. It's like we'd want to figure out when it starts to saturate, and that would help us figure out a lot. Oh my goodness. This is a giant plane. Doesn't want to stay molten. Maybe I should use some of that hot air gun. Goodness. Any VFD projects? To be honest, I don't have much use for a VFD, but the UPS that we're working on could be used as a VFD. That's more like an industrial beta kit. It's more like an off-the-shelf, you know, highly commoditized. Give it DC in, tell it what to do when it does it. We do more of this kind of nonsense, board level circuit design, but I suppose there's, yeah, I mean, like what we're doing is we're building something that looks a lot like a VFD on the output, where it's a filtered H-bridge. In the case of a VFD, the filter is the motor, but it's fundamentally pretty similar. Make a video when it arrives, set up a half bridge, drive from single to. Cool. Cool. That should be pretty sweet. Will that be similar to your, I think you shared a video, hopefully I'm remembering this right, and you showed it some gate drive coming through. I think you were looking at power transferred through it too, because you were thinking about shoot through. Oh. So kind of similar setup. That'll be cool. I don't know. Man, I'm going to totally butcher this name, and I'm really sorry, but it's like Satvik. Just curious, what were you hoping for with the VFD projects? I'm definitely open to it. Yeah, it'd be the BH curve that we're after. I typically like my core materials to come with a data sheet, but, you know, that's just because I'm boring and lame. Yeah, that's what I'm thinking. Yes, I forget. I think Ixis makes some, but you can get some. They're basically like an inverter in a can. where it's just filled with IGBT H's. Takes all the fun out of it though. No, they're actually a pretty good deal. Like cost for what you get, they're pretty darn good. Some of them are 3-phase, some of them are single. That does not look like it flowed well. Alright. So just gotta throw some test points on there and we're cooking with gas. Nice! Test points. Yep, we've got some, as long as I'm here, I'll filibuster a little bit. We've got some really exciting content coming. I'm pumped. You know, like I've said a couple times, I think I mentioned this in the last stream, but we're kind of coming to the end of the road with this. What is that? That looks out of focus. We're kind of coming to the end of the road with this prototype, and that means that it's time to finish up what we're working on, right? That means it's time to finish the larger design and get it out the door, start getting these cards in. And like, I've got to do some stuff with mechanical fitment and like software workflows and like power on sequence, designing that. And it's like, man, this is all super important work that is so boring. And I think we've got some excellent content planned for the next couple weeks while I work through those less fun, more important elements of this design. So we're gonna have some fun in the interim while I'm finishing up this design. For sure. For sure. I think actually the first video, it's like it's kicking off a mini series. So we're gonna be kicking off a mini series next week. Pretty excited about it. Let's take a ground. Sure. I don't think we really need that 5-volt test point here. I'll take the shutdown. Why not? I think that's all we need, because we've got voltage in, voltage out. Got ground and the shutdown pins. We can kind of shunt that over if we need to. Wait a minute. No, we need, this is actually the node that disables it. Hang on. Gotta grab the schematic. Hans. Great question. Which textbooks would I recommend for learning power electronics? Now, it's not explicitly power electronics, but in general, I love The Art of Electronics as just a general reference. Man, the way that I learned power electronics was just kind of like by doing this, where I'd like build stuff and then it would blow up, and then we'd build better stuff that doesn't blow up. Thanks, Tested. You think this looks cool? Dude, I love it. I love what it's turned into. This Frankenstein monstrosity. We've got some hopefully excellent boards. Our stream next week is gonna be fire. We're getting a shipment from JLC PCB, and we've got a really fun board that I haven't even teased yet. Yeah, TI app notes. Yeah, actually, I've been collecting some great. They've got a series of TI app notes that work well, but I really love just building stuff because there's a lot of parasitics in power electronics, and the higher your power level, the more those parasitics are going to come out to bite you and different topologies have different nuances that you need to navigate. So it's like there's the theory that you need to understand well to build it, but even once you understand the theory, there's a lot of little subtle nuances that are difficult. Fire? I meant fire in a good way. Fire in a good way, like awesome. Not fire in like a... It'll prevent fires. One of them will prevent fires. Also tested. YouTube auto flags swear words, so it hid that. I see it. I appreciate it. But I like to keep it clean here. So I'm not gonna release it, but I appreciate you. I appreciate you. So enable 1. Yeah, it's this. The shutdown is the internal node. I think I'll drop a test point on that anyway. Oh yeah. Oh yeah, just to like dev kit it up? Dude, seriously. Seriously, was it Hans? Oh, I gotta scroll up. Who is that? Yeah, is that Hans or Hannes? I could guess if I knew what country you're from, but I really don't know. By the way, welcome. I don't know if we've talked before, Hannes. But yeah, seriously, like, there are such great places that are so cheap to get fabs. I've used PCB Shopper. Yeah, fires teach you the weak spots. Agreed. There's so many cheap places to get PCBs built. So if you design your circuit board in something like KiCad, there's a lot of free softwares. I really like KiCad personally. Spelled KICAD. You get your Gerbers. I like to use a service called PCB Shopper. You go on that website. It lets you search and get a quote from 12, 15 different board houses. You go through that process. You figure out where you can get your board for cheap. You can order it. So I can put that in numbers for you. So like this massive board here, this is what? This is like a foot by a foot almost. This board cost me like $4 to have fabbed. So these little boards were like $4 for 50 of them. So they're pretty cheap. So depending on the size of your design, I mean, obviously there's still the components on the board that add cost, but like the raw PCBs themselves, man, it's basically free. Yeah! Yeah, so these were all from JLC PCB with their hot air solder leveling, which isn't the nicest surface finish, but it's fine for a prototype. The components that go on, yeah, that's totally dependent on your design, but you know, you make decisions when you're making component selections. Yeah, absolutely. It's to the point where when I want to prototype something, I don't even think about wiring it by hand or doing it on a proto board with point-to-point wires. It's just a waste of time at that point. Yeah. Yeah. So next week on the stream, I'm actually going to have some boards. I tried JLC PCB's assembly for the first time, but overall, so far, I am a huge fan. The pricing is so competitive. Their turnaround time is ridiculous. If the quality's good, I might just fall out of my chair. Because they assembled 10 boards for like, I think it was $10 or $15. Almost all the SMD parts, had them do all the resistors, all the caps, all that, you know, the hundreds of tedious parts that are just annoying. So hey, if they just went through that and crushed it, I'm going to be blown away because they did it for $10. So that's one way. If you're designing parts that are in their library and they've got most caps and resistors, or at least one you can use. Yeah, I don't know. Yeah, for assembly. I'm not sure. We're throwing a lot of numbers out there, but if you're talking about the assembly, yeah. I had some assembly done through all PCB. It was not a good experience. Let me just say that. Like their online quote was off by a lot. And then they just turn around, they're like, oh hey, pay us all this extra money. And I was like, how about nah? How about nah? And they were like, how about we meet in the middle? It's like, I hate you. But this was not like that at all. Their online quote was super accurate, and I feel like that's a function of they have these parts pre-programmed into their pick and place machines, and all they have to do is feed in the XY coordinates and go, boom, assemble this board, go. And it saves them a ton of time and a ton of effort, which in turn saves you a ton of money. So they're just being smart about the way they structure it. They're not doing anything super crazy. They're just commoditizing PCB assembly by having standard components that are always loaded in. Oh, yeah, you saw the video on all I don't know, I feel like I got a little upset during that video, but it really just makes me angry. Yeah, there's no reason for something like PCB assembly, there's no reason why an online quote shouldn't be accurate. Because it's something where it's not like assembling this board is super different than assembling any other board. There's pick and place and solder and reflow and stencils, and if you do it enough times, you get a sense for how much it's going to cost. Yeah, so definitely tune in next week if you guys are available, because I can't wait to rip that thing out of the box with you guys and take out the microscope, look at what happened. Like, I've got boards back where they had solder balls on top of the assembled PCB, like on top of parts. Like, they just weren't even careful with how they were handling the board at all. Cool. Alright, I think we're done. I think we're good. Just got it cleaned off a little bit so it's not sticky. Hey. I'll even turn off. No, you're gonna get upset when someone butchers your hard work. Thanks, man. I appreciate that. Yeah. So, Hannes, hopefully that answered your question. If not, just fire away in the comments. I won't be offended if you're like, hey, so you started answering my question and then you got super distracted. That happens. I acknowledge that freely. We're going to do a quick test for power ground shorts. Just a good thing to check. Yep. Alright, looks great. Okay. Where does that leave us then? I've got my list of parts here. Got the inductor on, got the diode on, got the caps on, transistors, and boom, everything is checked. So, smoke test first, then we're on to line and load regulation. In this particular instance, we've got two choices. We can either feed this supply from, oh man, no, so I actually goofed up. I goofed up in the schematic. We should probably talk about this first. JD, I was wondering for example electronic load. Yeah. You mean this guy here? You're looking at this electronic load? The one we got? If you've got a link, you can shoot it to us at our business inquiry email. You can get to that through our YouTube page or blast it out on Twitter. YouTube gets mad with links. But either way. But if it's this load, I like it so far. It hasn't blown up or anything. We were able to push it up to, what, 50 odd volts and a couple amps. We were pumping a couple hundred watts through it. Right. I need to see where our voltage is coming from, because there should be a 15 volt rail getting all the way over here from over here. Wow, I actually did that. How did I do that on a 2-layer board? That's a 5-volt. How did I? Seriously? Oh, is it? It must be running back right here. Yeah. So the reason why, the mistake that I made is I didn't realize this controller has an integrated LDO that feeds VCC. And so in the app note, they diode OR this. So on startup, we can start up from the battery. It'll kickstart itself, which will in turn turn on the 24, which will in turn turn on the 15, and then the 15 will backdrive VCC so the LDO doesn't burn a ton of power. But right now, VCC is just tied straight to the 15-volt rail without a diode. So when we try to power it on, it might be loaded too heavily from the rest of the system. So that means that we're going to need to power on the 15-volt rail first, or get a diode in series. I think I'm just going to power on this rail first. Okay. We're fired up. No problems so far. Okay. And then I'm going to need to get the rest of this wired in, which will involve a couple test clips and maybe zoom it out a little bit so you guys can actually see something. So basically what I need to do is get the scope hooked up to the output. Let's see, is this still? Dope. Missed. There it is. At least close enough. My new thermal imaging finger. Thermal imaging finger. Did I just touch it? Did I look around and oh? What do you mean? I don't burn myself with electronics sometimes. Yeah, I think that was my thermal imaging finger. Yeah, sometimes you do stuff without even thinking about it. It just becomes second nature, for better or worse. I think in this case it might be worse, but hey, that's alright. Okay. So I want to hook this on to monitor a 24-volt pre-diode. I added in a test point here so I can monitor the output voltage without loading it. Yeah, pretty sure that was my thermal imaging finger. That's a good one, man. We need ground. Got all these stinking test points hanging off the ground. And I can't remember where my second alligator clip is. Hey, look, an alligator clip. Can you guys tell I'm excited? I'm pretty excited. I always love. Alright, so let's get this in volts. We're just getting random noise right now. It's not enabled. But if we come in here and clip on ground, I know we're gonna have all this series impedance and it's gonna be gross and nasty and terrible. Alright, there it is. So now hopefully I'll kick on that supply. Can you guys see that? Not quite. Oh, thanks, man. I'm glad you enjoyed the video. Should we get the RGB fan out? Should we get it going? Who wants to see the RGB fan going? The red, green, blue fan? It just wouldn't feel right. It just wouldn't feel right. I'm pretty sure that dev kit's still laying around here. Come on. Where's that Arduino? That's what I get for cleaning the shop. There it is. There it is. Alright. Alright. Getting the fan going. This is ridiculous. I love it. Right. There's the fan. Let's get the data. Am I trying to plug it in backwards? No. There it is. And we need a couple clips. Power, ground, and data. I'm glad that you guys like the red, green, blue LEDs. I'm glad that you like them. You got the ground. Just gotta feed in the 5 volts. We'll have to toggle it a couple times. What's your guys' favorite color? Because this just picks a random color on boot. So I can cycle it a couple times until we get an acceptable color. What are you guys feeling today? It should be 5. There we go. It's like, that's like a light blue. There. Got a red. Kind of feeling the teal. You guys fine with teal? I'll get this put over where it actually might help something. There. That's not so bad. Wife says blue. Dimensions. Here, let me get this calibrated instrument. We're at 10.5 freedoms by, that's inches. 10.5 inches by 9.25 inches. Oh, I guess I can do that in millimeters. It's right on the other side of the ruler. That's more helpful for literally everyone. It's actually designed in millimeters too. So it's 23.5 millimeters. No, 23.5 centimeters. Sorry, metric. Metric's hard, okay? By 27 centimeters. Yeah. But you guys probably read the ruler better than me. Thanks, man. Wait, is that actually blue? Or is that teal? Well, I'll see if I can find like a true deep blue. Oh, there it is. There's the true deep blue. Wife said blue. Hey. Orange. Alright. Alright. I'm having too much fun. I'm having too much fun. Oh, come on. Does this even have orange? It might not have orange. I thought it just picked a random... Alright, whatever. We'll leave it on blue. Really? Black and white? How do you even do that? Can you watch in black and... Anyways, let's power it on. Let's see what happens. So we're feeding 24 volts in. That's not a good sign. I mean, nothing seems to have catastrophically failed, but our output voltage is 8 volts. I could have mispopulated a feedback resistor. We're gonna need to probe around a little bit. Let's get this tweaked. There it is. That's really interesting. Any ideas? Happy wife, happy life. I don't know if you're kidding. I feel like that's actually pretty decent advice. Yeah, it's like a joking, not joking kind of situation. Anyways, alright, we're getting out the cheapo voltmeter here. I just want to take a look at a couple critical nets here. Want to look at the voltage on the feedback pin. All sorts of things. Okay. So we got ground. This is going to be our voltmeter. So shutdown is on. Oh my goodness, idiot. I hooked that onto the wrong node. Hopefully the enable signal still works. Oh, I probably blew the crap out of our hot swap controller. That's not good. So what I did is I applied that to our 24 volt enable pin. Thankfully the current was small. What did I just do? I was passing a lot of current through our poor little BJT. Good thing we put the fan on it. Yikes. Yikes. So it's that, if you're on the schematic page 7, that was enable 1, not enable 1. Yeah. We just put 24 volts on that. Yikes. Okay. Oh no. We might have blown up our controller with that. No. Probably not. Okay. Let's look at the shutdown pin now that we've removed that. We're getting 0.3 volts. That should be pulled into V in. What? I must have mispopulated a resistor or something. Because that's not right. We're in 27 volts in. Our 132 is a 1 meg. We're getting no. How does that even? Whoa, 24 volt enable has voltage on it? This is not supposed to be disabled by default. I wonder if I have an external pull up and an internal pull down. Did I do that? If anyone's got the whole schematic open, did I add a pull up and a pull down to that? It looks like I might have, because I'm an idiot. I mean, yeah, I just made a simple mistake and I'm frustrated. Alright. Okay. I pulled 24 volt enabled to ground and our output voltage went up a little bit. What does that even mean? Why are we getting 8 volts out of this thing? Yeah. I think we need to get some scope probes on this thing. Let's get some scope probes on this thing. Okay. So we want to monitor same net. Volts per division. Seeing about 10 volts. Okay. Channel 2. That's on the 24 volt sense. So, okay, seems fine. Channel 2, let's probe shut down. So, not shut down is low, which means that we are shut down. Why are we shut down? That doesn't make any sense. What? Do you see what's happening here? Look at what's happening to our output voltage. What? Is this just like a really, really, really slow soft start? You guys seeing this? The divider has 64K pull down and a 1 meg pull up. Oh, that's on the shutdown. That's okay. That's setting a UVLO threshold. That one's setting the UVLO threshold. I was wondering about the BJT. Enable an R136. What's on the other side of that off-page connector? Is there a pull-up? Yep. Yeah, he was looking at R132 and R133. That should set our UVLO to 18 volts. Oh. So if I pull that down, that pulls that up a little bit. If I set that to 5 volts, weird. So if I pull this hard to 5 volts, it doesn't impact the output voltage. When I pull it to ground, my question is, why is the shutdown pin not getting pulled to ground when I bias it through this resistor? I may have blown up the BJT. Let's try replacing that. It's got a lot of things to turn off here. Alright. What do you guys think about that? Yeah, it might be really slow. It really could be. NPN transistor MMBT 3904. Let's give it a shot. I mean, I did apply 30 volts where there was meant to be 5 for an amount of time that was longer than 0 seconds. Yes, you are correct, as in enable 1 into Q20. Because there's a test point outside of the visible schematic. So I'm wondering if I added a pull-up out there as well, like perhaps R58, wherever R58 is. Cool. Yeah. Thanks, Tested. See you in a sec. We'll be here. We'll be here. At least until it works. Come on now. So what I'm doing is I'm carefully resting the iron across both terminals of the transistor. That does not look like it wants to melt. Might need to use the hot air gun to get this thing off. It's kind of ridiculous. Little 3-pin South 23. Wow. Alright, guess we're using hot air. Yeah. Yeah, I don't... It was through R136, but even so, the amount of current we were pulling through that thing, it was probably not happy. Trying to not melt my scope probes. Realistically, I should just take them off. Let's take off the scope probes. Let's not melt the scope probes. We can melt the rest of it. There it is. Transistor off. Whoop, whoop, whoop. Throwing things. Getting so mad I'm throwing things. I'm just kidding. I'm good. I'm good. Alright, let's get this thing on there. A little dab of solder. We'll be off to the races. Alright. So now when we pull 24 volt enable to ground, hopefully we'll see shutdown change state at least a little bit. And if we don't, I'm gonna be really confused. Okay, so gotta do the same power on sequence. 20. Whoa. What? Why? Why you no power on? Oh, wrong plug. Okay. So here we go. We've got 5 volts on the 1. The blue probe is on 24 volt rail. Yellow is on shutdown. Shutdown is 0 volts. Makes sense that we are shut down. Just gotta rescale this a little bit because I swapped my probes. So hopefully we should see this come up to something reasonable. In this case, I'm gonna pull it down to ground, so when we power on, hopefully the UVLO will change to something good. Okay. At least it's being reasonable now. So it's either in one state or the other. We're getting 0 volts out, which makes a lot more sense than... Oh, wait a minute, there's no power applied. 28 volts in. Same garbage. Oh, wait a minute, no. Different garbage. I think shutdown is now measuring some reasonable voltage. What are we getting? We're getting 1.59 volts. Yes, so that transistor, we blew up the transistor. And that was a big part of our problem. Increasing the input voltage, it appears that we're actually regulating to 8 volts. Did I totally hose up my resistor divider on this? Picture in picture blocking view. There you go, man. Alright, let's think about this. We want to have a 24 volt output. Oh my goodness. I bet that R147 is way too big and I grabbed the wrong power of 10. I'll put money on it that I either put on a 51K or a 511K. I'm gonna put money on that. Okay. Just gonna do a... Really, we have to take this out of circuit to measure the resistance, but it should get us rough order of magnitude. Because 5K11, there's a lot of resistors in this. So that'd be R140, R147. That seems kind of reasonable. It says I'm getting 2.4K. This little guy should be about 500 ohms. Looks about right. R146 should be about 100K. Given that this is in circuit with other stuff, that actually seems about right. Which is weird. Okay. Let's check on our feedback voltage. Feedback voltage. I'm sorry, what? What? What do you mean you're out of range? Oh my goodness, I know what it is. Is that scaled? I'm getting 24 volts out. Why is this test point getting 8.3? What? Oh, what? Oh. Wait a minute. Wait a minute. Are we backdriving the feedback with the other rail? I'm half tempted to unplug this and see if we stay alive. Should I unplug it and see if we stay alive? Yeah. Yeah, it is. So that means the only way to test this is just to pull out the power plug and see if we stay alive. So I guess the reason why I did that is because I didn't want this regulator to be pulling a ton of current, and it's not. It's shut down. It must just be in its minimum. Should I just rip out the power and see what happens? I think I should just rip out the power and see what happens, because that sounds radical and fun. Alright, I'm gonna hook up input voltage monitoring as well. I'm gonna monitor input voltage, output voltage, and we're just gonna go for it. Sound good to you guys? Here's a scope plot. I think we're good. I think the controller's alive and well, because we're still getting 8.33 volts out, and the quiescent current is very, very small. It's less than 0.1 milliamps for sure. So here's what I'm gonna do. I'm gonna set this to 50 milliseconds per division. And I'm going to trigger on the rising edge of our output voltage. And that's channel 2. Channel 2, rising edge. Is channel 2 AC coupled? Yep, it's like that's not right. We should be getting 8. Okay. Channel 1 is not shut down. This is going to be awesome. So that'll be, what is that? 5, 10, 15, 20, 25. Alright, so we'll see that. The level. I'm sorry, what? Channel 2, I said. You guys ready for this? Okay. I'm nervous. But I think it just might work. Single shot capture. Gonna pull out the power plug. If the lights go out, something's wrong. Okay, something's wrong. Okay. I think that I want to trigger off the pink channel on the falling edge. Trigger pink channel falling edge. That'll be our input voltage. That'll basically show us channel 3 falling. Single. Alright, let's see what happens. Why? Why you know? Wait a minute. Wait a minute. I think I know. I think I know. When I applied that voltage, I might have damaged the ideal diode controller. No, but our FET would still be forward biased, so it should be. Man, this is confusing. Okay. So now I notice that we're getting proper 0 volts. What is happening? So our controller was getting warm, but I have a feeling that has more to do with the LDO than anything else. The weird thing to me, or one of the weird things to me, is that our scope is like not capturing whatever's happening, and I really, really want to know. Like, what? It says that we're just like fine. Okay. Let's get tabs on this 24 volt rail. I think what it is we don't have a good trigger. .24 volt net. So we're at 24 volts. Pull it out. what are we at? 4. Why does that drop down to 4 volts? Okay. I think I'm going to tweak our feedback network to do it right, because this thing's driving me nuts. So I'm going to make this thing regulate just its own voltage. We're going to make it be a happy little camper so we can make sure it's working before we rip it out. That'll let us isolate the hot swap controller and the rest of this garbage. That should be easy enough to do. Just gotta swing a diode, pull over a little jumper wire. That won't take long. Americanoed. Nice. Closer in the sense that we ripped out the power and nothing good happened. So what I'm going to do is I'm going to rotate our resistor a little bit, and I'm going to pull the feedback from the regulator side of the ideal diode controller. I think the reason why I put it on the other side is so that as the 24 volt rail drooped, this rail would just come up, meet it in the middle, and take over. Maybe that's how we'll get there eventually, but hey, I gotta figure this out. So that's generally how I like to do it. That's what happens in our switchover from the PFC to the battery full H. Basically just one being enabled pushes the other one to minimum duty cycle, which is cool. Holds it disabled, basically. Yeah, we'll get there. We'll get there. I think the reason why our controller was getting so hot is because of that internal LDO. So it was feeding the 15 volt rail from an LDO down, yeah, so that's why our controller was getting warm. That's why I didn't want to leave it on too long in that state. Alright, there's stinking diode is important. Yeah, so that blinking might have... Thank you. Thank you for that. It's our multimeter kindly reminding us that we're taking too long. Alright, well, that seems ideal. Just giant wire floating about, carrying our feedback. What could possibly go wrong? I also noticed I didn't add a feed forward on this converter for some bizarre reason. Not sure why I wouldn't do that. Okay. I'm sure you guys are dropping ideas in the comments. I'll get to those in just a moment. I'm gonna get this soldered in. Okay. So now we've got there, I went and ripped it off the board. Okay. Okay. Same thing, only different. Yeah. Sorry, I was rambling a little bit. I was talking about something unrelated. It's the PFC and the full H. The minimum duty cycle of the TL594 controller is what I was referring to. I keep doing that. That's the one for the supply that's off. Okay. All right, let's get our scope probes back in place. So 24 volt rail should be 0 since we're not giving it V in. Shutdown should be 5 volts. What? Yes, it is. And then, don't really need this probe right now. Yeah, so we'll just turn it off. Then we'll get our supply there. Kick it on. That looks pretty good. Again with the 8 volts though. But why though? What is this thing doing? Did I grab the right? Wait a minute. Why am I tying burst enable to feedback? That doesn't seem right at all. I feel like that should be going to ground. That seems like a pull up, pull down sort of situation that should super not be tied to V feedback. Did I just whiff? Did I miss? Oh, I see. The compensation components are hanging off a different pin. That's why. Alright, I'm pulling up my phone here. Searching for the data sheet. LT 3800 EFE. Wow. Data sheet isn't tied together? That doesn't make any sense. Maybe if I know what burst enable means more. I'm sure it's got an explanation. Alright, we need to search for burst enable. There is one result. Oh, I see. It's called soft start disable / burst enable. Any ideas here? I mean, okay. Here it is. 3800 employs low current burst mode functionality to maximize efficiency during no load and low load conditions. Burst mode is enabled by shorting burst enable to S ground. Burst mode operation can be disabled by shorting to either feedback or VCC. So that sounds fine. Okay. And what is the feedback voltage this controller regulates to? 1.35 volts? No, that's the VLO threshold. 1.2. 1.2 at the feedback pin. That's what we're looking for. Okay. 28 in, that makes sense. Basically 0 volts at the feedback pin. down. 1.7. What did I just say their threshold was? That seems pretty close to their EVLO threshold. 1.35. Okay. Maybe we'll just give it a little more voltage and see if she springs to life. It's looking like a no. 1.75. So that should be good. So now we've disabled the converter. Come on now. We're down to 7 volts. Enable. Weird. Okay. Now my question becomes, is that an actual 8-volt output that we can pull current from? Or is that just like garbage? That's my next question. Let's seek an answer to that. Need a good ground test point. That looks as good as any. Shorter to ground for burst mode, shorter to V feedback. Enable reverse current. Inhibit. Sounds good, man. Thanks for the extra detail. I was reading quickly, so I think I skipped over that detail. I don't have a good way to tap off power directly. Alright, let's plug in the electronic load. Here we go. I think I've got to power cycle this one more time, because I need to add on another place to grab some voltage. I think this is going to be Man, the last stream we did, I feel like everything just went really, really well. They can't all do that. Sometimes you gotta have a little bit of fun, a little bit of debug. I feel like that's what we're getting today. We're getting our healthy dose of debug. What do you guys think? Do you think we're going to be able to pull current from that 8-volt rail? Or do you think it's just like some kind of leakage? Or I think we might have torn this resistor apart. Yeah, it's only got one terminal left. The other one's on the pad. Grab a new 100K resistor. Maybe I should tape that down or something. I'm gonna grab a piece of Kapton. This is my first time using this controller, but nothing is telling me that it's probably broken right now. It seems like it's working, right? It's not getting excessively hot. It's actually trying to pass some power down. Yeah. It is coming up really slowly. That's a good point. It's a good observation. Yeah. I think that adding a load to that is going to be very telling, because it's either going to just immediately clamp it to ground, or we're going to be able to pull like amps of current at 8 volts on a 24 volt regulator, both of which I think would be very telling. Though I suppose we haven't looked at the switch node. Not sure why. Maybe we should do that. Alright, got that resistor tacked on. Going to connect our electronic load. Danger, danger. Let's see what happens. Okay. Electronic load is connected. It's seeing 0.67 volts. Turn on the output. We're seeing the same thing. Slowly climbing up to 8 volts. Very slowly. Oh, sorry, that's kind of off screen. Here. Yes? Can you guys see that? 5.57. No, but I can do this. Now you can. Okay, let's add a little load. Nope. No current carrying capacity. Immediately clamped. Okay. I feel like that's a sign. Let's check out our switch node. Dead. Okay. Well, that's why we're not getting power. It's not switching. Okay. Alright, so we're getting our 24 volt input. Could be something with the bootstrap. No, well, maybe. Not voltage in. Nothing out to the inductor. That should be ground. That is ground. That should be 15 volts. Alright, let's just disable, re-enable. Doesn't really seem to change much when we change this. Never really tries to start. It's pretty weird. Yeah. Yeah, well, you know, kind of getting a that's not right. That's not right. The other side of our what? Alright. This could be a case of... Oh, that's our switch node. I see. Why is our switch node at 5 volts? Where's that coming from? Yeah. So our top gate is at 5.6 volts. Well, to be honest, some of those solder joints look a little anemic. Maybe I just need to reflow the IC. Maybe I'm missing a critical connection. It could be as easy as that. It could just be a solder defect. So, I think it's worth a shot. So what I'm going to do is I'm going to come back here, add a little more solder to a couple pins that seem to be lacking it. I'm sure that I'll add 1,000 solder bridges because this part is tiny. One of the pins that looks anemic, by the way, is where the bootstrap capacitor connects. So if that's actually not connected well electrically, that might be a sign. Okay. Like I checked it for continuity, just not positive. Being very careful. This is a very fine pitched part. Come on. Need more flux. Brilliant. I think I just shorted every single pin on that side of the part. Excellent. Come on. One stubborn short on this side. Ugh. Doesn't help that I'm chained. There we go. Pretty sure we got that resolved. Yeah. Alright, we're gonna need some wick on this other side. Oh, sorry guys, picture in picture. Yeah, I can get that webcam out, or the microscope. Yeah, microscope. Checking whether, yeah, it's not, the gate driver's internal. Whether you get power, but it seems rises. Nope, can't believe we only just now tested push on it. Oh yeah. Oh, the one that was, yeah, anemic. Sorry, it's hard to always keep tabs on the comments when we're in the throes of it. Yeah, look at that beauty. Power it on, see what happens. Yeah, that'll be great. Alright. I don't want to steal all the solder. Just want to steal some of the solder. Come in here with a little bit of paste flux. Let's try to reflow that. I can't see a darn thing that I'm doing. How's that look on the scope? Still got one short. Is that down over there? Yeah, it's on that end. Just pushing it around. Durr. All right, let's do a little more solder. If this controller survives all this nonsense, mad props to Linear Tech. Oh my goodness. Oh. There. Okay. Got it. Let's check the other side. I like that. Don't you dare power it on. Every single pin shorted together. Why not? It looks perfect. Oh, I'm a jerk. Anyways. Oh boy. Oh boy. I really need a better microscope stand so you guys don't. That one looks pretty good. No shorts over there. Sweet. Let's give that another try, shall we? Okay. Maybe? Stranger things have happened. Let's get our 24-volt monitor. Let's get our shutdown monitor. Let's enable the supply. Yeah, I think that's 0.5 millimeter pitch. That's a pretty fine part. Okay. Powered on. Go. Got the fan going. Yes. What do you guys think? Think we're gonna get power? I don't know what I think. I think I'm confused. Hey, wait a minute. This is way better. Guys, I think that might have been the problem. Because we're not floating the output. Okay, I turned on the electronic load and I think it might be back driving some power. But we're not floating up to 5 volts anymore. I don't think it's cooked. I think she'll be right. All I gotta do is flip on the supply. Dude, I think we're coming to life. Ugh. Okay. Okay, there's one more thing I want to try. This shouldn't matter, but right now we've got a pretty massive ground loop. I just want to tighten that up. I want to come back to a closer ground pin for that. And I'll use the weaker reference for my scope probe. Now it appears to be exactly the same. So, looking at this part, yeah. It's hard to show you everything at once, but I suppose when the scope's boring, there's no point in showing you the scope. Yeah. We can test the Hotspot controller. That's a good point. Maybe we should do that. So if I go ahead and I feed this back to over here. What was all that? Why? Oh, it probably didn't like that V out was higher than V in. Yeah, the controller was probably not. Wow! Woo! That one was hot. Huh. Well, now the controller's cooked. So, should really invest in a real thermal camera. Woof! That one's smarted. Can you guys see that on the camera? There's a nice little red dot. Oh, man. Well, I think we can safely remove the controller now. And we can test that hot swap controller for sure. Alright, I only have 2 of those, so we gotta be careful. We are dangerously close to have to cut off the stream early on a failure territory. We're 1 controller away. Yeah. Alright. What am I doing? I don't need that. I need this. Yeah, that's brilliant. Ever. Oh boy. Yeah. So good thing we have that ideal diode controller in there. Backdriving this supply? Super no bueno. Sigh. Burnt my hand many a time just by trying to make my fingers work as thermal sensors. Oh yeah. I heard a weird noise. I was like, I wonder if that controller's getting hot. Touch the controller. Oh yes, it was a little bit red hot. Just a little bit. Welcome, Sai. Glad to hear from you, man. Oh. Yeah, man. That's just disappointing. Oh yeah, that was super bad. Because there's in this controller there's like an output high side current sensor, and so basically we were probably backdriving power into the controller through that interface. Well, we'll add that to the trophy pile. We needed more trophies. I mean, yeah, that was on purpose. You believe me yet? Alright, let's test out the Hotspot controller then. Oh, yeah, fans don't start too well when they're laying on a bunch of cables. Okay. So we should be able to just take our power supply and hook this up to ground. Nope, that's not ground. Hook that up to ground. Hook that up to 24 volt output. Let's make sure we're set to 24 volts. 23.5. Dope. This should be fine, right? What? Why are my... This should be fine, right? Oh, we're passing 2 amps or something. What are we passing 2 amps through? Our diode's not on backwards, is it? No. It's possible that the rising edge transient of the supply is like messing with stuff. It's also possible we blasted our hot swap controller. Yikes! So with 0.3 volts, we're passing an amp. I bet you one of our gates is enhanced. I bet you it's our... both? I don't know. I don't know, man. When you take your gate driver out of circuit and you just got FETs hanging out, yeah, that seems like a good time. Okay, what is this gate voltage at? This gate is at 180 millivolts. This gate is at... What are we passing current through? There's like nothing. Well, we could always just yeah, gate drive is floating. Multimeter said almost nothing. Oh, sorry, zoomed in. Multimeter was saying hundreds of millivolts. That is well below the threshold voltage, but I suppose just to be safe, I can just short them out, see what's what. But we were talking like 0.3 volts, like shockingly close to the threshold voltage of our diode. This guy right here, D61. Yeah, caps should be alright. Those shouldn't be cracked. One second. Apparently there's something weird in the apartment. I'm gonna check that out. BRB. What's up, guys? I'm back. No problem, just a toaster oven blue breaker. We're good. We're good. We're good. Based on the thump I just heard, I think it might have blown again. Whatever. We don't need toast that bad. TP70 to ground in diode mode, both ways. Alright, let's do it. TP70 in diode mode, both ways. Yes, apartment is not on fire. That's the way I like it. Well, see, the report that I heard originally is, whatever you just did, stuff is getting shorted out. And I was like, nothing that I'm doing should affect any other room of the house. Oh man. I think this is 20 amp. It's a big one. It is a GFCI though, so it might have been leaking some current through ground in a way it shouldn't. Oh! Dude, good call. That's a dead short. TP70 to V out is a dead short. What is that? Is that supposed to be? Oh, yes, it is. Okay, yeah, it's just a node. You said TP70 to ground? So, positive direction, that's one diode drop away. Does that make sense? Yes. Because we're pulling through D61, through Q22, through L4, through RM141, and out to TP70. Let's do it reversed. This is the... Oh, wait a minute. Wait a minute. I had my polarity backward. This is through that... What? The shot key can't be that good. Yeah, it looks like a back-to-back junction. What? Oh, sorry guys. Sorry guys. Back-to-back junction. What? Why? What failed? D62 is not populated. Should I take D61 out? Did one of our transistors fail? Do we think one of our transistors failed? Could be. We might have... One of our FETs just totally blasted. That is an option. I don't know what would have caused it to fail. That's dope. No, those all... Oh, that's not a good sign. Let's do diode check. Looks like our high side FET might have failed conducting. What? Diode check mode? No, that's 0.5. Looks good. 0.1 from the shot key. That's the direction that's the problem. What is going on with that? So testing the diode in the forward direction. We're getting the shot key. Flip it around. Why are we getting a volt to ground on the switch node? A volt to ground on the switch node. You guys seeing this? I'm not seeing this in the schematic. Yeah, I mean, I could just take it off. But that's all to the V24. So that FET. What in the world? You guys see this diode lighting up? Wait a minute. That means this is shorted to ground. This node is shorted to... Alright guys, I'm figuring it out. I'm figuring it out. I think I know... I think I'm figuring it out. Okay. So I was doing the diode check. Like, who's that? Psy? JD? No Corp? So I was checking out the ideal diode controller. I went and I put my... Oh, come on. I need to make it so you guys can see the diode. I put this there. I put this in the reverse bias junction. You guys see that little light? Underneath my probe, you see that green light turning on? Yeah, that little green light means that V plus is shorted to ground. And I'm putting money on it that it's through our ideal diode controller from when we overvolted it. And perhaps that was the cause of our problem the whole time. It was me putting 30 volts on the wrong pin. Thankfully I got plenty of spares of that. This is a fun stream. I'm really enjoying myself, and I think it's absolutely awesome because we have a challenge to overcome, and I think we're still going to do it. I think we've got a chance. Okay, let's see if that resolved their short. So if that LED turns on, I'm going to have some questions. Oh, short is still present. Okay. We're going to have to start taking parts off the board till that short goes away. There's no shorts back where we pulled off that component. What in the world? Just to be clear, that is ground, right? Yeah. So, what in the world? Guys, I am perplexed. Because, so I come over here to this side of the junction. We test ground. We get a diode. What are... Okay. I want to try to power this thing on again. Because... like No Corp was suggesting, this is a very complex circuit we're trying to strap into. And eliminating variables like this hot swap controller should have resolved that short. It really, really should have. Alright, I've got 3 volts. Yeah, it was the hot swap controller. I'm able to power on now. So that hot swap... No, FETs seem fine. So I figured it out. The reason why we're seeing that diode in the other direction is because it was going through the hot swap FET, through this diode to ground. See, but now that I've removed the dead hot swap controller, we're just going through the body diode of that FET, and we're fine. So yeah. Alright, should have just replaced all the silicon involved when we had that failure. That was my bad, guys. caused some casualties. Caused some casualties. Back drove the 3800 whatever, blowing it up. That's alright. We'll get it. We'll get it. Which body diode? There's a lot of FETs and diodes and stuff we're talking about. Where do you guys think the problem is? Because I personally feel like I think I got this one in the bag. I think we swap it around. Or basically replace the old Hotspot controller. I think we put that LTC whatever back in circuit and it's gonna fire up. We must have been triggering some kind of overcurrent protection because we're basically shorting it out. If I were a power supply, I wouldn't like being shorted out either. Alright. Pin 1. There it is. Gonna do hot air on this. Just drop some fresh solder on those pads. And we need a little bit of flux. And I'm just gonna do that same 24 volt test to make sure that we're good. Once that's confirmed, we can populate the rest of this controller and be on our merry way. I'm not exactly sure. It might have been backfeeding through the body diode. Because this body diode is forward biased out towards the 24 volt rail. And then these are both pointed up. I don't know, man. There's too many intrinsic and intentional diodes in this system. Alright. Hot swap controller's populated. Just gonna give it a moment to cool down. Powered on. Look at us go. Alright, we're gonna check out the hot swap controller. Just make sure that it's working right before we move on. That'll be a quick voltage check. I'm just gonna make sure we're driving the gate VGS to something positive. Which terminal's the gate? Gate is 1. Source is 3. So that means we want to check this voltage. Should be positive. Hello? Hello? What? What? Why am I getting no voltage to any pin? 17 volts. Is this thing getting hot? Here I burn myself and I go and follow it up. There it is, 17 volts in. 18 volts out. And what are we getting here? 18.14. What? That's supposed to be driving the... Something doesn't smell right to me here. Something doesn't smell right to me. Alright, I'm gonna probe this one over here. So now we've got same thing, only different. Seeing the same behavior. 0 volts in. Okay, so we're seeing 24.36 volts out, and we are seeing 24.38. So that FET is fully enhanced. Unplug it. $17.5. 18. Why is that FET not enhanced? I have it populated in the correct orientation. Solder joints look good. I'm just going to increase the input voltage a little bit. I'm going to see if it's easy as that. 24.02. 24.6. We're still seeing that 0.7 volt body diode drop. But why though? Oh, no, 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 no. Thought I had it, then I didn't. Wait a minute. We might be holding it disabled. I think we might be holding it disabled because our jumper is not installed. Did it just snap to life? Bet it did, because when you disable an ideal diode controller, what you get is a non-ideal diode. You can't take the body diode out of circuit. So hopefully that just latched us in. If we look at VDS, yes, we're now driving the FET. Yes, okay, this is working. The ideal diode controller, 12.6, 24.6. Okay. Oh, what was I changing? JD, I was changing a lot of things. What I was just doing there is I tied this jumper to ground because we've got to pull up, defaulting the backup supply to off. And I've got to short that out to enable it. Okay. That was the last thing I changed. It's time to bring our switch mode power supply controller back into the mix. Means you gotta get the hot air gun out again. We're gonna need a little bit of luck, a little bit of skill. Okay, a little bit of skill and a lot of luck. Alright. Votes in the comments. How many of you think that I hosed it up with that, the first mistake? How many of you think this is just going to come to life and work perfectly? And we just wasted like an hour debugging a supply that was fine because I shorted it out. Not wasted. Spent. Spent. Because if you're having fun, it's not wasted time. Alright. Gotta spin my pin 1 indicator around. Yeah. So if this converter works, I'm going to feel pretty good about the design overall. Because if this converter works, that means that we could literally short the output for like a while, and it would just kind of deal with that, and it would be fine. And it wouldn't blow up your FETs, and it wouldn't mess with anything. It would just be fine. Boy, that would be refreshing. Alright, just want to get a little bit of flux on there before we call it good. Alright, so that should be a near perfect solder joint. Let's get that one under the microscope for a moment. I'm going to try to freehand this. That looks pretty good to me. Oh, sorry guys, I'm a little shaky. Looks very good to me. The other side of this. Excellent as well. It's fun. Oh, thanks, man. Thanks, Tested. I'm glad you're having fun. Okay. So our feedback is currently disabled because some goofball undid his rework. Yeah. Wake up. Alright, feedback has been established. I'm scared. Let's do it. Let's punch it. JD, you said, yeah, that would be nice. I can't remember what that's about. If you could remind me, I will happily do whatever that is. Okay, so just trying to get the electronic load in the frame. Man, I need a bigger bench. I'm like tripping over myself. Okay. Okay, so we got that. Can't quite. Maybe if I just, doop, there it is. Let's get the DMM on. What do we want? Output voltage? Do output voltage. Gonna enable the supply because I'm not gonna forget about that again. And then let's get our DMM wired in. And the electronic load. Let's get these both wired in. Okay. Ground. Got this set to 22 and a wimpy current limit. So I don't want to blow this thing up. Uh, 26. Sweet. Okay. It's time. Let's see what we can see. Retrofit electronic load to the RGB fan. Yes. No, but I wish they were. If they were Pomona grabbers, they would work way better. These are cheap off Amazon. That's why they're slipping all over the place. Pomona grabbers are expensive, but man, they grab and they don't let go. Also, I don't know why nobody else makes the grabbers or test hooks or anything. I don't know why Pomona has like a death grip on that market. But yeah, they're crushing it. They're doing a good job. Alright. We're powered on. Whoa. Was that the right? Where's? Alright, there it is. Boop. Okay, electronic load is on. Board is on. I'm so scared. Whatever. Let's do it. Oh my goodness, 23 volts. It was fine the whole time. Oh, it was fine the whole time. It was fine the whole time. Ugh. Alright, frustration out. 23.19 volts. Ugh, it's nominally 23.1. It's... Ugh. Ugh. I'm so pissed. Anyways. So now if we unplug the board, does it stay on? Yup. It works. Sweet. So we have to start it from that external input because of the 15 volt nonsense. We'll add the diode so it can start up from the batteries. Yeah, so it'll keep itself running off battery power. Yeah. Yeah, it's working. Let's do a quick load test. I don't have enough time to run through the whole suite that I had planned because the debug took a little longer than anticipated. But I at least want to run this thing through the paces, get up to the 4 amp output, and yeah. Measure the efficiency, make sure it seems to be working well. Cursory glance. We can get the scope probes on there too. Take a look at the ripple and transient response. Just run through a couple quick ones. I mean, we can't just like get it working and then not have some fun with it. And I think I'm gonna swing. I think I'm gonna swing that resistor back around. So I'm going to disconnect. Oh, I'm scared to disconnect the batteries. Because I know... Yeah, I'm going to have to do some serious power sequencing tests with this. Yeah. Because I know if I do it wrong, that controller smokes. So I guess what I'll do is I'll pull this, and then I'll pull that. That's the safest way for us to power down. Because if that ideal diode is too slow... Yikes. Yeah. What do you mean? You don't think I can just leave well enough alone? You think I've got to just mess with stuff? Yeah. Maybe I can't just leave well enough alone. Okay. There it is. So there's where you can tap off a load directly on this supply. By the way, I strategically set this to 23.1 because I know that's enough for all our converters, and that'll keep this FET normally not enhanced because it's a 24 volt input. So basically, I'm letting the ideal diode controller automatically pick this one last. So it picks input 1 or input 2, doesn't care. And then the batteries are third in line. Well, it's cool that it works. 50 volt input is quite a wide range. Alright. Little dab of solder. Alright. So hopefully this is kind of the same thing, only different. Yeah, it looks fine. Alright. Now power on secondary source. Let's take a look at the voltage on the output. We're down at that 5-volt minimum. Unplug this and kapoop, pops right up to 23 volts. Sweet. So basically, this converter is just sitting idle whenever you've got the regular input. It's just chilling. It's like, whatever, man, we're good. We're fine. We're sitting here chilling at our standby. We're just chilling at 6 volts, but the second it's needed, it goes whoop. 23. Cool. I like it. So let's capture that transient, because that'll look really fun on the scope. So we want to look at the 24 volt before the diode. So right now that's 23. Plug that in and yep, comes down. Nice, it's great when things work. Now it's working. You say, it works. Stop playing. But I just finished the work. Now I get to have the fun. Yeah. That's rough. I feel you, man. All right. So, going to picture-in-picture, because now we got something fun to look at. We are just using channel 1 and channel 2. Channel 1 is the output voltage. Channel 2 is the... Wait a minute. Channel 2 is supply voltage. We want pre-diode and we want post-diode. So we do want channel 3. I'm going to put this on the same scale. This is going to be a really fun scope plot. And then we want to trigger on channel 1 rising. Alright. Channel 1 rising. That should be fine. Okay. Time scale is probably reasonable. Single shot capture. And I'm going to pull out the power. There it is. So, what do we see? What do we see? Just want to pull his position in so we can see it a little better. So we can see blue scope probe as input. That's just coming from our DC air lab supply. Is our third channel connected? So I was hoping to capture if there was any. No, it's not. Okay. I'm going to connect the third channel now. Connecting that to the 24 volt rail. Single shot capture. Pull the plug. There it is. Let's take a look at how that looks. Oh, look at that beauty! Look at that beauty! So we pull the plug and it just ramps from 24 down to 23.1. And when we get down to 23.1, our buck grabs it and takes over. Oh, yes. Yeah, that's great. That's awesome. Yeah. Yeah. So clearly there's only one more thing to do. We need to load this thing. We need to grab a load on the 24-volt rail and just do the same thing but loaded, right? Because reasons. So we're getting the electronic load. I'm gonna set this to, what are we gonna do? Start with an amp. Or 1.6, sure. 1.6 amps, let's make sure our current limit's high enough. .32 volts on the DC input. Single shot capture. Nice. So same thing, just faster time scale. Since we are now a little more of a transient there. The blue is again the input voltage, so that's fine. We're just taking a gulp of current from the electronic load and it's taken up. That's really what it is. So we got down to the 1.5 amp load. Our minimum voltage, what was that? Gonna be on channel 3. Minimum voltage was 21.7. That's fine. As long as our 15 volt rail doesn't brown out, we're good. So, yeah. Let's try that under heavier load. I also want to get this on a ground test point so I can monitor the output voltage. So let's do what? This is supposed to be able to handle 5 amp or 4 amp output for sure. Not sure how true that is, but should be able to. 20 amp? No, this isn't 20 amp. This only needs to supply the input power from here. So 10 amps is the maximum on these, but that's really overrated. Because what this needs to do is this needs to supply enough power to charge the batteries and run the UPS. This converter only needs to run the UPS because if we're charging the batteries from the batteries, we're just burning power. So, there we go. Dang, we're pushing some watts through this thing. Calculator. Calculator. Where is my calculator? There it is. Whoa. Got so mad I threw it. Alright, let's do a quick spot check on efficiency here. So we've got a 32.4 volt input times 3 amps. We got 97.2 watts in. We've got 23.76 volts out times 3.7 amps. We have 87 watts out. Bippity boppity, 90% efficient. Unsurprisingly, those FETs are warm. Controllers, a little warm. I don't have any thermal vias directly under the pad. The thermal vias are off to the side because the power dissipation of this part's relatively low. But maybe I'll drop a couple V's in there. It's warm. It's not uncomfortable to hold my hand on. Whew! Those FETs are a little uncomfortable to hold your hand on. I've got some other FETs. I've got some nicer D-squareds I can put on there with lower RDS on. Or that's a D-pack, sorry. D-pack FETs. I might swap on the nicer one. But, yeah. Should be able to get this up to 4 amps, no problem. Let's try a 5 amp transient, see how that goes. I think 6 is about where things will start getting hairy. I lied. We hit the current limit on the supply. Oh yeah. Yeah, we're pumping way too much power out of this thing. I've only got 30 volts, 6 amps. Yeah. Anyways, let's try that again. Single. Go. Yeah. Yep. So I think I'm going to change out that high side FET, because of course most of your losses are on the high side one. So make that high side FET a little nicer. Optimization, we can maybe get this thing up to 95% efficient. Yeah, get that heat down so we can get that output current up. Yeah, let's go for proper 5. 5 amp test. Yep, we're good. Cool. You guys got any other thoughts? I'm loving this so far. I'm loving that we got a UPS. We have a UPS that can keep itself alive. That is very important. If the UPS can't keep itself running, how is it supposed to keep other stuff running? But yep, AC fail, don't care. If I want to not have so much of a glitch on this scope, we can definitely move that feedback node back over so we're always regulating. Then it'll just be a little bit cleaner. I don't know. I think it'll be alright. Tears of joy. Thanks, JD. Yeah, it feels good. Feels good to load it. Have good regulation. I've got a bump. Oh, wait. One more test. Before we go, one more test. What do you guys think? One more test? Can we do that? You alright with that? One more test because I want to test the maximum input voltage. I want to test the maximum input voltage of this thing. And the only way we're going to do that, it'll kind of defeat the purpose. The only power supply I have that can supply that much voltage is the battery charger. So we're going to have to use our battery charger to feed power to this guy. And I don't remember. I don't remember what voltage that's set to. I should double check. This thing can allegedly handle up to 60 volts. I don't plan to pull it much above 55. 55 is about where it's going to tap out. But really, normally we'll be floating more in the high 40s kind of range. Do we need to enable this? Oh, we need to give it 24 volts. Yes, of course. Yes, of course. Woo! That is a spark. Don't hot plug power supplies, folks. Yeah, I don't have two though. I could Series 2 bench supplies. That's one of the best things about bench supplies, is they just don't care. Man, this hook is like super. I need to invest in Pomona test hooks. These bend way too easily. Alright, the V out is 54 volts. That's perfect, actually. So, yeah. This is going to be super hard to test because the only voltage we can really probe is this, and it's going to be like idling down at 8 volts. But that's kind of a worst case, because if this supply is going from 55 volts down to like basically 0, that's pretty intense. So we're gonna pull this up to, let's see, 100% duty cycle is 49 volts. So we're gonna set this to 49 volts by tying this to 5 volts. Here's 5 volts. So now we should be getting 49 in the output. We're gonna walk our way up to that maximum. That's 51. Close enough. All right. All right. We're gonna switch this guy over to our output. We're gonna load that guy down at 8 volts. I don't know why it's all a guy. I think I'm just excited and my English is getting worse. Alright. Let's fire it up. And let's use our benchtop supply this time. Gotta set it down to 24. Let's do it. Alright, we're getting our 8 volts out as expected. I don't even know what's going to happen because this feedback, we're just getting minimum duty cycle. So it's not even regulating. But it's not blowing up, so there's that. Yeah, I don't know. Cool. Hey Dave, no problem. More floor work. We're actually just about to wrap up here. Got a battery charger working. Yeah. Hopefully, pulling this to 5 volts didn't blow anything up. Yep, so I just disabled the output. Pull this over. Enables the output. Probably pull a spot of current here. Nah. We're just sitting at minimum duty cycle. Cool. Yeah, so the only way I can... Oh, I know what I need to do. I need to Whoa! I thought I needed to undervolt the input. Something started squealing, though. What was that all about? Yee! What was that? Which converter's not happy? Seems like we're fine. I don't know. Something started squealing. I have a feeling what it was the current limit from the battery charger tripping because of the 2 amp limit. I have a feeling it was a combination of the current sense there playing poorly with the rest of this. But that's cool. We're running with a 50 volt input. Oh, wait a minute. Yeah, that was kind of silly. Yeah, that was kind of silly. 51 volts. Brown this out. Yeah, it's that one. Battery charger gets grumpy when we try to pull that kind of power from it. But let's turn up the output voltage, or input voltage a little bit. Let's start up at 55 volts. Cool. Nice, Raphael. Welcome. Yeah, we're just about to sign off here. What we're doing is testing this. So if you guys got any last minute questions, now's the time. we're really wrapping this one up. Next week though, we're gonna have a lot of fun. We're getting, like I said, those boards from JLC PCB. We're gonna be able to evaluate their budget assembly for the first time. It's gonna be awesome. Sorry, Raphael. Do you want to see the power transfer? I can show you the power transfer. I'll show you the power transfer. All right, it's fun. I don't want you to go away empty-handed. Everyone needs their cool factor for the day. And this is pretty cool. What I can do is crank that. Yep. That ought to do it. So now get our scope probes back over. As they say, one scope plot a day keeps the doctor away. That's definitely what they say. Oh, whatever. Here, I'll show you this. There. That's an old one. It's basically, the output voltage of this converter ramps up, grabs a hold, and stabilizes the 24-volt rail when the 24-volt rail fails. Super sweet. Anyways. Yeah, next week we're going to have those boards from JLC PCB. We're going to dive into one of those in a little more detail, dig into it. A couple weeks later, we're going to be strapping the PSOC 6 DSP onto the old inverter prototype, and we're going to test the inverter control loop on the new microcontroller with the bumped up performance. Hopefully our frequency tolerance will be tightened, our output voltage transient response will be improved, and the sinusoidal nature of it will be more perfect. So it should be a higher quality sine wave that we're getting out of the UPS. So yeah, no problem tested. I really enjoyed this too. I had a lot of fun hanging out with you guys and fixing this problem where when I did that, I probably should have just replaced all the silicon and just been like, all right, I probably blew everything up. Let's replace it. I didn't. That's my bad. Whatever. Oh yeah. It's going to be fun. We've got like probably a month or so of finishing it up before we really get the full beast. But it's close. I got to work through some subtle details like, fitting this thing into a box. I agree though. It's going to be mint. It's going to be awesome. Going to be able to daisy chain a bunch of these together, generate three-phase conversion. Like, man. We got a lot of success here, and we worked out a very important kink in the architecture. We got the new buck design that is going to carry us to a lot of success. So, no problem, Dave. Yeah, it'll come up soon, whenever YouTube finishes processing, but it's an absolute blast. Thanks for being here, everyone. Hope you learned something great today. Hope you guys enjoyed the journey of debugging the wide input range step-down buck converter with us. Our next stream is going to be same time, same place, November 9th, 8:30. Hope to see you guys then. Cheers. Yeah, I'll go fix that toaster oven. Yeah, will do. See you guys. Thanks for joining me. Had a lot of fun.